Okay, this is going to be the video for Calculus 3, Section 14.8 on Lagrange multipliers, which is optimization of multivariable functions that are subject to a constraint or more than one constraint in the domain. Let's take a look at the notes here. And this is the last section in Chapter 14. We did find that if we wanted to find the absolute max or min over a region in 14.17 or 14.7, we said that we would have to check for local max and min, right? But then we would also have to look at the boundary of everything in the domain. So is this actually presenting? Let me present this again. We'd have to look at the boundary in the domain because the max or min on the surface might occur at the edges of where we're allowing the region to look at in the domain, as well as it potentially could be where the first derivatives are zero, right? But that can be pretty cumbersome, especially if you have a complicated domain edge. And that really assumes that you've got a region in the domain, right? But there's other ways to express constraints for the domain. They could be that we only allow certain values of the x and y, say in a two-dimensional domain, that are represented by a curve, right? Or maybe there's more than one constraint, so we need a more flexible way to test for max and min with some kind of constraints more generically defined. And that's where Lagrange came up with just a beautiful method. I think this is just such a neat thing. Now, we introduced this as a procedural process back in brief calculus in the Calc 3 introduction chapter, but we didn't really explain why it worked. And so we'll be able to now in Calc 3 explain why this method is working. Okay, so this is called optimization with constraints using the method of Lagrange multipliers. And in the last section, we said if a function has a constraint to establish the absolute max or min, we have to find the local extrema, right? But with the Hessian determinant procedure, but also check the values on the constraint boundary, right? So a more general method is this. Let's say that we have a multivariable function where we have a domain which is two-dimensional, so x and y input, and then z is the output. And maybe we represent that by just graphing the domain and showing level curves that show the values of x and y that give particular output values of the function. So any xy pair on this red curve here gives an output value of 7. Any xy pair on this curve gives 8, and so on. Right? And maybe we're trying to figure out, what would be, say, the maximum value or the minimum value of this function subject to a constraint, right? I can see that as I'm moving from level curve to level curve, right, the output is increasing, right? So, but if I have a constraint, if I knew that I could only allow xy pairs on this curve, like we'll define a constraint curve like this, then I could say, okay, as I move along that curve, right here I've got maybe 6 and then 7 and then 8 and then 9 and then 10 as the output value, and then it starts to decrease again so that this max value occurs right here at this particular xy where the output value is 10, right? But there is a particular point here which is going to reach as high as it can on an increasing slope like this. All right, so here's the idea that Lagrange noticed, and that is that if you were to draw such a curve that represented the constraint in the domain, then wherever it touches its maximum point, and this is also true for mins, if these numbers were going down, wherever it touches that optimum point, right, the constraint curve and the level curve are tangent to each other, right? They share a common tangent, right? And what that means is the normal vectors, right, for each of those curves would be in the same direction, right? The normal vector that's perpendicular to the tangent here would be in this direction, right, for the function itself, the multivariable function, and the normal vector for this constraint curve would be in this direction. So they're aligned. One is in one direction, one's the opposite direction, but they're in the same kind of line, all right? And those tangent vectors are the gradients of those said curves. So this red vector here is the gradient of the multivariable function, and this blue vector here is the gradient of the constraint function, okay? Because we know gradient is in the domain, right? So both these functions are in the domain, even though this f represents potentially a third dimension, right? So if the gradients are parallel, that means that one of the gradients can be expressed as a scalar multiple of the other. So we can say that the gradient of the multivariable function f is a scalar multiple of the gradient of the constraint function, which we're going to call g right now. Okay, and that means that we could say the gradient of f is equal to lambda gradient of g, where lambda is a scalar multiplier. And that lambda is what we call a Lagrange multiplier. So it's a scalar multiplier that allows one gradient to be a multiple of the other. All right, so at the optimum point, this relationship will be true, right? All right, we can use that fact to locate max and min functions subject to constraint, and you can actually extend this to any number of input variables and also to any number of constraints. So if we just have a single constraint, we could say that the gradient of a vector f, multivariable function f, of any input number of variables is equal to lambda, scalar multiplier, times the gradient of a constraint function. Okay, now there's some issues with the constraint. The constraint has to be some sort of a function that uses the same values as the domain for the function, so x, y, z, right? And you have to be able to express it as some function of x, y, z equal to a constant. So a constant on the right side, but this can be anything. It can be trig functions, polynomials, rational functions, anything, right? And then the only other constraint is that the gradient has to be non-zero anywhere over the region of consideration. Okay, so we can use that to find the max. Let's take a look at an example so we can see how this would work. All right, so let's say we have a multivariable function f, which is a function of x, y, and z. Actually, you know what? That's a typo. This is a function of only x and y. So let's say it's just two-dimensional to start with. F is a function of x, y, and it's x squared plus 2y squared. Okay, and then I'm going to say, all right, so we've got a surface above the xy plane, and I would like to find the extreme values, so both the max and the min value of this function, right? But instead of allowing any xy pair, I'm only going to allow xy pairs that make this constraint true, basically that they're on a circle. So what I'm really saying is, I mean, just to kind of visually see what's going on here is I have my xy domain down here, right? I've got my z equals x squared plus 2y squared output. And I'm saying, okay, if you were to graph this, this would produce some sort of a surface, right? In fact, actually, it would be some kind of a elliptical paraboloid of some kind. So there's some sort of a surface, right? And then what we're saying is I don't want to find the max or min value for all xy's. I want to find the max or min value if I restrict myself to only the xy's that are on the circle of radius 1, right? So above that, there's some kind of curve here, and I want to know the max and min of the value in this restricted part of the domain. All right, so it's not necessary that we graph it because we're going to use a computational procedure to find it. So the first thing we would do is define the variables or the functions. So we know the original function we're optimizing, f of xy, is x squared plus 2y squared. They gave us that. And then the g function is also given in this problem. It's going to be x squared plus y squared because it has to be everything on the left equal to a constant. So whatever's on the left is the constraint function. All right, so then what we're going to do is try to solve this as a system. The gradient of f has to be lambda times the gradient of g. So first we'll start by taking the gradients of those functions. So the gradient of f requires us to take the partial derivative. So fx would be 2x, fy would be 4y, and therefore the gradient of f would be the vector 2x 4y, right? And then for g, right, we need the partial derivative of g with respect to x, which would be 2x. The partial derivative of g with respect to 2y y would be 2y. And that makes the gradient of g equal to the vector 2x, 2y, right? All right. And then this relationship says, all right, the gradient of f, so let me write it again. The gradient of f is lambda gradient of g. And that means that the vector 2x, 4y must be equal to some scalar multiple of the vector 2x, 2y, okay? And because vectors have multiple components, we can set all the x's and all the y's, and if there was a z, all the z's together to start forming a system. So we're going to make a system of equations. This first one is going to say 2x has to equal lambda times 2x. That's matching the x's, right? And then we also have to have that 4y has to equal lambda 2y, right? That's a system. Unfortunately, we have three unknowns, x, y, and lambda. So we need a third equation to come up with a solution. And the equation is that we're going to use the complete constraint, right? When we did the gradient of g, this constant doesn't get used, right? But it does get used when we include the constraint itself as another equation in the system. So we also add any constraints into the system to form a system. So now we have three equations, three unknowns, x, y, and lambda. And if we solve for all of them, then we're going to be able to identify the possible xy pairs where maxes and mins could occur. And if we have more than one, then we can plug those into the original function to figure out which one is the max and which one is the min. Okay, so to finish this, we're going to have to solve this system. Now, the system part, the calculus part, Calc 3 part's done at this point. From the rest of this is now basically an algebra problem. Okay, so let's look at the algebra steps to solve that. There's no standardized way to do that because typically we have nonlinear terms, so I'm not going to be able to do RRF pretty much ever in these kind of cases. But let me number these equations. So this is 1, 2, and 3. And let me just show you using elimination or substitution, kind of, any way you can think of to try to come up with answers. This is one way you could go about it. I'm not saying this is the only way, but this is the way that occurred to me and also was the way that Ms. Dastu did last year in class. So let's take equation 1, which is, if I got everything to the left, it would be 2x minus lambda 2x equals 0. Which means I could factor out a 2x and get 2x times 1 minus lambda equals 0. And that would be true when one of two things was true. Either x equals 0 or 1 minus lambda equals 0, which would be when lambda equals 1, right? So if these are true, it's going to make equation 1 true, right? So then I have to also figure out, with that condition, what would have to be true to make equations 2 and 3 true as well. So what I'm going to do is I'm going to take equation, let's see, in this case, I know that x is 0, so I could use equation 3 to figure out what y would have to be. So if I use equation 3 now, x squared plus y squared is 1, and now if x is 0, then that means 0 squared plus y squared would equal 1. That would mean y would equal plus or minus the square root of 1. So we have x is 0, y is 1, or we have x is 0, y is negative 1, right? And just to make sure that this is true, if I now go to equation true, can I have this xy pair and get a lambda? That would work as well, because now I know what y is. So if I go to equation 2, I know that 4y has to equal lambda 2y. So if I plug 1 in for y, I would have 4 equals lambda times 2, and that would mean lambda is equal to 2. So this is one possible solution. If we have x is 0, y is 1 with lambda 2, that's one possible solution to the system. Okay, let's look at this part next. So if we have 0, negative 1, right? So I'm going to use that same equation, 4y minus or equals lambda 2y, to find what the lambda is, make sure there's a lambda. So that would be, if I plug negative 1 in for y, I'd have negative 4 equals lambda times 2 times negative 1, which is negative 2, which would also give me lambda equals 2. So another possibility is x could be 0, y could be negative 1, and lambda could be 2. Okay, so we've got two possible places here of x, y's that I need to probably test and make sure that that could be where the max and min is. So let's further pursue this case. What happened if we started with lambda equals 1? Well, if lambda equals 1, then I could let's switch to equation 2, because 2 evolves. This came from equation 1, and lambda is also a part of equation 2. So if I use equation 2 here, 4y equals lambda 2y, and then I plug in 1 for lambda, I would get 4y equals 2y, and therefore, let's see, that would be true whenever y is equal to 2, right? No, that's not right. We would have to say 4y minus 2y equals 0, right? So you could factor the y out, and you would get 4 minus 2 equals 0, right? And so actually the only way that would be true is if y would equal 0. Okay, so if y equals 0, then I would need to check to see what the matching x is. Now I've used equation 1 and 2, so I'll need to use equation 3 now. X squared plus y squared equals 1. So if I make y 0, that would be x squared equals 1. And that means x could be plus or minus 1. So my two possibilities here would be x could be 1 with y 0, or x could be negative 1 with y 0, right? And lambda is 1 in all of these cases. Okay, so I've got, all right, now I've got 4 possible xy pairs down here where the max and min might be occurring up here on the surface. Okay. Now that all came from starting with equation number 1. Okay, let's take, what if we were to start with equation number 2? Okay, let's just see that we don't get anything else. If I were to start with equation 2, which was 4y equals lambda 2y, and do that kind of same thing, 4y minus 2 lambda y equals 0, we could factor out a 2 and a y, and we would get 2 minus lambda equals 0, which is going to happen when y is 0, which I've already explored, right? Or if lambda is equal to 2, which I've already explored. So that's not going to give me any additional numbers, right? All right. And I think all of these cases here that we've already counted are the only cases that would make, let's see, would make this equation true, right? X squared and y squared have a relationship here, but we've already accounted for that because we've used that here. So I'm pretty confident at this point that we've seen the total list of possible values, right? So what are my xy pairs where I might have a max or a min? And so we're going to just plug all those values into the function we're optimizing, right? So my list is 0, 1, 0, negative 1, 1, 0, and negative 1, 0. And I'm just going to try all those in here to find out what the output value would be. So if I use 0 and 1 for x and y, that would be 2. If I put 0 and negative 1 there, I would also get 2. If I put 1, 0 in here, I would get 1. Negative 1, 0 is also 1. So it looks to me like the maximum value of this function, the max f, or I can maybe write it this way, f max is 2. And that occurs whenever we have 0, 1 or 0, negative 1 as the xy. And the minimum value is 1, and that would occur whenever we have 1, 0 or negative 1, 0. All right, so that is the way a Lagrange multiplier problem works. Okay, now if you remember, I know it was quite a while back, this is exactly the sort of problem that we did back in brief calc, and we did stuff like this, where we had a little bit more procedural way to do it because we didn't have the gradient defined, but it was basically these same steps. All right, so the other thing I want to tell you is some interpretation of what's going on. Just we've already kind of tried to sketch it, but I actually have some pictures here. So here's the picture of the domain, right? Here's that surface, right, above our circle. And what we just found out essentially is that the constraint is this circle here, right? These red level curves would look like this, and it just kind of grazes like this, right? There's 2 spots where we hit the maximum value of the level curve, which is 2, and there's 2 spots where we hit the minimum value of the level curve, which would be 1. Right? What's really happening on the surface is an elliptic paraboloid or a circular paraboloid, right? And above these spots is where we have the minimum, where the z is down here and then again down there. And above these spots, that's where we have the maximum value on the surface. All right, not super important that you can picture it all, but we need to be able to do the computation part. All right. Okay, so far we haven't really done anything that we couldn't have done back in brief calculus, although we have a more elegant way to define it. But the real beauty of this is that not only can the domain have any number of input variables, x, y, and z, but you can have more than one constraint. Okay, so let's say we have a function, multivariable function f of x, y, z, but we have 2 constraints, a g constraint curve and, oh, that's another typo. There should be a different letter. Let's call this h, another constraint curve, okay? Then each of those would have to be scalar multiples of the gradient for the function. And that means we would maybe use lambda for the multiplier for the first one, and then some other letter, like, for example, mu as the Lagrange multiplier for the second constraint. And this could be extended to any number of constraints, right? So it's very flexible. Okay, so I've got one last problem here to work, and this is the last thing we're doing in the video. But it's quite involved. The algebra is quite involved. The calculus is not too bad. But this one's a little different because we're not going to be given the equations. We have to figure out the equations. So what this says is find the max and min volumes of a rectangular box whose surface area has to be 1,500 square centimeters, but whose total edge length has to be 200 centimeters. All right, so let's draw a picture of what we're doing here, and maybe we can add some variables for what could vary. Okay, we have a three-dimensional box. Okay, something like this. And actually, I assume it's actually a closed box. So let me draw it as a closed box. Okay, so we have a three-dimensional box here. And let's define some dimensions here. So just arbitrarily, let's call this x, y, and z. We're trying to find the max and minimum volumes. What's going to cause that to change is if I change the dimensions. So I need to make the dimensions variables. Okay. So the first thing is I would need to find the function that I'm trying to optimize. That's going to be the volume, right? And the volume is therefore a function of x, y, and z. And the volume of this box would just be length times width times height, right? So x times y times z. So an easy function to do the optimization on. But we're going to have these two constraints. The first constraint is that the surface area has to be 1,500 centimeters. So the area, maybe we could call that function A, okay, is going to be, well, let's see, we'll have an area here, right, which is x times z, and there's two of those surface areas, so two xz's. And then there'll be an area on the front here, right, which is y times z, but there's two of those, a front and the back, so 2 times yz, and also a top and bottom area that's xy. Right, so that's a constraint because that has to be forced to be equal to 1,500. Okay, and then I have another constraint, which is the edge length. So the edge length are all these edges. So if you look at just this, like these x's, there's 1, 2, 3, 4 edges that are of length 4. So the edge length, maybe we could call that E. That's going to be equal to 4 lengths of x, but also 4 lengths of y, and also 4 lengths of z, right? And that has to be equal to 200 centimeters. All right, so I've got two constraints here, and I've got my multivariable function that I'm optimizing. So what we're going to be doing for the Calc 3 is saying that the gradient of the volume function has to be equal to lambda times the area constraint plus, let's call it mu times the edge constraint. Okay, so that's an E there, edge. All right. Edge constraint. Okay, sorry, not just that. I didn't write that quite correctly. Gradient of A and gradient of E. Gradient of that constraint plus mu times the gradient of the E constraint. So we're going to have to find all these gradients first. Let's go ahead and do that. I'll do that in, let's do that in red. Okay, so the gradient of F, that would be the partial derivative in the x direction, which is yz. And then for the y component would be the partial derivative in the y direction, which would be xz, right? And then the partial derivative in the z direction, which would be xy, right? The gradient of the a vector, or the a function, would be the gradient of this, the partial derivative of all this with respect to x, which would be 2z. There's no x here, but there's an x here, plus 2y. That's fx, or that's ax, right? The partial derivative of a with respect to y, hey, there's no y's there. There's a y here, so 2z plus 2x, right? And then the partial derivative with respect to z would be 2x plus 2y plus nothing. All right, and then we also have to have a gradient for the e vector, or the e function. So in the x direction, the partial derivative is 4, right? In the y direction, it would be 4, and in the z direction, it would be 4. Okay. All right. So let's go ahead and keep going here. I notice already that I have, unfortunately, a mistake. Oh, maybe not. Actually, let me make one little change because I want to make it match here. You could take this equation and just divide everything by 4. So I'm going to actually do that. Let me rewrite this equation, just call it x plus y plus z equals 50. That will allow me to not have to carry this 4 all the way along. And that would actually allow me to make this vector 1s instead of 4s. I don't think that's hugely important, but I did that when I wrote my key out, so I want to be able to compare as I work here. All right. So now I've got my 3 gradients, and now we're going to make the gradient function itself, the Lagrange function, this right here. The gradient of f, so yz, xz, xy, must be equal to a multiplier lambda times 2z plus 2y, and then 2z plus 2x, and then 2x plus 2y, plus a different scalar multiplier, let's use mu, times the gradient of the other constraint, 1, 1, 1. And then I'm going to start working on my system. So my system will match the x components, the y components, the z components. So that would be that yz has to equal lambda times 2z plus 2y plus mu times 1. And then the y components would be xz has to equal lambda times 2z plus 2x plus mu. And then the z component would be xy has to equal lambda times 2x plus 2y plus mu. Now we have 5 unknowns and only 3 equations, but we're going to go ahead and put in the 2 constraint equations. And actually, let me simplify this one as well. If we divide everything by 2 here, right, this would end up being, in fact, I could have done that even at the beginning. Let me do that right now. If I just made this 1, 1, 1, and 750, then this would all get much, much easier, right? These would become 1s. I actually am going to do that because the less, there's already enough writing in this problem to, so if I can make this easier at the beginning, that would be, I think, preferred. Okay, so actually this is then z plus y, z plus x, x plus y, plus mu times 1, 1, 1. And that means that for our system, we have yz has to equal lambda times z plus y plus mu. Xz has to equal lambda times z plus x plus mu. And xy has to equal lambda times x plus y plus mu, plus the 2 constraint equations. So I would have xz plus yz plus xy must be 750, and x plus y plus z must be 50. That's an equation, or that's a system with 5 unknowns, but we have 5 equations, so there should be unique solutions. All right. Now, to solve this, quite a bit of stuff goes on here. Let me go ahead and, the Calc 3 part is done at this point, but let's number these equations. We'll call this 1, 2, 3, call this one 4, and this one 5, okay? And I'm just going to start playing around with things, mainly using substitution or elimination on pairs of things. And again, because I have mixed products here, I'm not going to be able to do RREF, really, where you can't multiply this out and get the right number of rows and columns. So let's take equation 1 and subtract equation 2. If I took yz equals lambda z plus y plus mu, and I subtracted this equation, lambda z plus x plus mu, then I would get over here, I could factor a z out, y minus x, and over here, right, the mu's would cancel, and I would end up getting lambda z minus lambda z, which goes away, but lambda y minus lambda x is going to be lambda times y minus x, okay? Which really is only true if z equals lambda. So that's one thing that has to be true for equations 1 and 2 to work simultaneously, Okay, and if I did kind of something similar with equations 1 and 3, where I subtract 1 and 3, so I take yz equals lambda z plus y plus mu, and then I take equation 3, xy equals lambda x plus y plus mu, and subtracted these equations, I would get, there's a y in common here, so I could factor that out. Y times z minus x equals, let's see, the lambda y's would cancel and the mu's would cancel, and I'd be left with lambda times z minus x. And because the z minus x's are here, the only way this equation is true is if y is equal to lambda. So z must be equal to lambda and y must be equal to lambda. That's kind of interesting. Okay, what I could do is, now that I know that, I could start substituting for z and y in the other equations. So first, let's substitute into number 5. So maybe I'll change colors here. If I substitute y equals z equals lambda into equation 5, then I'm going to get x plus y, which is lambda, plus z, which is lambda, equals 50, right? And that means that x is equal to 50 minus 2 lambda. So I've got a relationship between x and lambda. And then if I substitute y and z lambda into equation 4, then I would get this. I would get, let's see, x times z, which is lambda, plus lambda for y, right? And lambda for z. Is that right? Lambda for y, lambda for z, right? Plus x times y, which is lambda, is 750, right? And so that's going to give me lambda squared, let's see, plus 2 x lambda terms equals 750. And therefore, I could say, okay, x has to equal, let's see, if I subtracted it, it would be 750 minus lambda squared, but over 2 lambda, okay? So I have two expressions here that relate x and lambda together, right? You could substitute one into the other, or set them equal, essentially, right? That's what I'm going to do. I'm going to set what these two expressions for x equal to each other. Let me change colors a little bit because we're getting kind of confused, or confusing. Okay, so let's say that since both of these are equal to x, they're equal to each other. So I could say, all right, 50 minus 2 lambda equals 750 minus lambda squared over 2 lambda. And if you multiply both sides by 2 lambda, you would get 100 lambda minus 4 lambda squared equals 750 minus lambda squared, which you can rearrange to get 3 lambda squared minus 100 lambda plus 750 equals 0, which then means you could use the quadratic formula. And when you do the quadratic formula, you end up getting 50 plus or minus 5 times the square root of 10 over 3. Okay, so I'll let you do that intermediate step. Right, but now that I have lambda, and I have two specific values for it, the plus value and the minus value, I could plug that value back in for y and z, and then also here to get x. So y and z, let me actually do this, right? So there's two values for lambda. Let me switch to, there's 50 plus 5 square root of 10 over 3, or lambda can equal 50 minus 5 square root of 10 over 3, right? And then y and z are both equal to lambda. So that means that y and z are also equal to those same numbers, 50 square root of 10 over 3, or y and z is equal to 50 minus 5 square root of 10 over 3, okay? And then for x is just 50 minus 2 lambda. So if you take 50 minus 2 times that lambda expression there, if you'll trust me, that turns out to be 50 plus, well, let's actually work it out. want to make sure I get the numbers correctly set with the sign. So this would be 50 minus 2 times lambda, which is 50 plus 5 square root of 10 over 3, right? Or you would have x is 50 minus 2 times this version with the minus. All right. All right, so really crazy. Basically what that means is there are, let's see, we can have the plus version. How many different versions are there, right? We have this version. So if we were to make our big table here, I'm going to have a lot of space here. So for the x, y, z, right, we could have x is 50 minus 2, 50 plus 5 square root of 10 over 3 for x. And then y would be 50 plus 5 square root of 10 over 3. And z would also be 50 plus 5 square root of 10 over 3. That's one possibility. Or you could have x be the negative version, 50 minus 2 times 50 minus. So this changed to a minus here, square root of 10 over 3. And in that instance, we have 50 minus 5 square root of 10 over 3 and 50 minus 5 square root of 10 over 3 for the y and the z. And then you can plug those in to find the function curves, and it turns out that you get, let's do it, let's just try one real quick. I'm just going to do it in the calculator. So the original function, x, y, z, was x times y times z, right? So I'm just going to multiply these three things together, right? So I guess I need to have the actual numbers. Let me get decimal equivalents for each of these. So 50, okay, 50 plus 5 times the square root of 10. And this is all we're doing is just filling this out. So you don't need to watch the rest of this if you feel like you don't want to watch me struggle to get a decimal answer here. But this is the method of Lagrange multipliers. Let's see, we would have then 50 minus that number. So this would be 6.1257, okay? And this would be 5 plus 5 times the square root of 10, and then divided by 3. This would be 6.9371. And this is also the same, 6.9371. Okay, the other version, 50 minus 5 times the square root of 10, and then divided by 3 times 2. You know, 50 minus that number gives me, wait a second, is that right? 50 minus 5 times the square root, 10 divided by 3, okay, times 2. Yeah, sure enough, 50 minus this number would be 27.2076, and then 5 times the square root of 10. 50 minus that number divided by 3 is 11.3962, and this would also be that. So the two volumes are 6.1257 times 6.9371 times 6.9371, which would be 294.8 approximately cubic centimeters, right? If this was in centimeters, yep. And then the other one would be 27.2076 times 11.3962 times 11.3962 would be 3,533.5 cubic centimeters. So the max volume occurs when you have this particular arrangement for x, y, z, and the minimum volume, would be this when you have that particular arrangement. All right, so pretty intense, right? But the kind of beauty of this is that you can have any number of variables and any number of constraints, and the same procedure would work. The tricky part is it's hard to solve, right? Unless you use numerical techniques, it's hard to program to solve a system like that. But you could. There are methods to do that numerically. Right? The key, though, is this idea right here, that the gradient of the function you're optimizing is equal to the scalar multiple times a gradient of the sum of a bunch of terms for each constraint where you multiply the gradient of the constraint times the Lagrange multiplier. All right, that should wrap up that example. And that's all I have for section 14.8.